Time crystals represent a completely new phase of matter, expanding our understanding of what is possible in physics. Ordinary crystals like diamonds or salt have atoms arranged in a repeating pattern in space. This regular arrangement of atoms creates a structure that looks the same if you shift it a certain distance in any direction. A time crystal is a structure that repeats itself at regular intervals in time rather than in space. Imagine a system that changes its state in a cyclical pattern, like a clock ticking. In a time crystal, the system's state returns to its initial condition after a specific period, creating a time-based repetition. Unlike regular crystals, time crystals exist in a state that is not in thermal equilibrium. This means they don't settle into a resting state, but instead keep changing perpetually.
What exactly are time crystals? This new phase of matter is not just a theoretical curiosity, but an actual entity that exhibits properties defying the conventional laws of physics. Unlike ordinary crystals, which have a repeating pattern in space, time crystals repeat themselves in time, meaning their structure changes constantly, but periodically. This phenomenon is akin to having a clock that ticks without needing energy. It's a perpetual motion at the quantum level. The discovery of time crystals has opened up new avenues in the study of non-equilibrium phases of matter, pushing the boundaries of our understanding of the physical world. The journey of time crystals began with a speculative idea proposed by theoretical physicist Frank Wilczek in 2012. Wilczek, intrigued by the symmetry properties of ordinary crystals, posited the existence of materials whose lowest energy states, ground states, are in perpetual motion. This was a radical departure from existing theories which suggested that ground states are typically static. Wilczek's proposal set the stage for a new realm of physics, challenging established norms and inviting scientists to rethink the fundamental principles of time and matter.
The first successful demonstration of time crystals came in 2016, when two independent research teams at the University of Maryland and Harvard University created conditions under which time crystals could exist. These experiments utilized systems like trapped ions and nitrogen vacancy centers in diamonds to reveal the oscillatory ground state of time crystals. These initial experiments were crucial not only in confirming the existence of time crystals, but also in showcasing the methods through which these elusive states of matter could be studied. One of the most riveting characteristics of time crystals is their ability to remain in perpetual motion. This is because they exist in a non-equilibrium state, constantly oscillating between different states without ever settling into thermal equilibrium. This behavior is radically different from most systems observed in nature, which tend to move towards a state of minimal energy and motion. This perpetual oscillation defies the classical laws of thermodynamics and opens up fascinating questions about the fundamental principles governing energy and motion. Time crystals represent a form of symmetry breaking, specifically the breaking of discrete time translation symmetry. This means that while traditional systems are invariant over time, time crystals repeat their state over fixed intervals, creating a pattern in time rather than in space. This concept can be visualized by considering a pendulum that, when nudged periodically, adopts a motion that synchronizes with these nudges. This synchronization in time crystals, however, is inherent and does not require external force once initiated. Time crystals are not just a theoretical marvel, they have practical implications too. In the realm of quantum computing, for example, time crystals could potentially provide a new way of constructing qubits that are less susceptible to decoherence, thus improving the stability and reliability of quantum computers. Moreover, their ability to maintain consistent oscillations makes them perfect candidates for improving the precision of measurement devices like atomic clocks and gyroscopes, which are pivotal in navigation and timekeeping technologies.
Future research directions. The research into time crystals is still in its infancy, with much left to explore. Scientists are now looking into various physical systems where time crystals could potentially be realized. This includes research into superconductors, Bose-Einstein condensates, and photonic systems. Each of these systems offers unique challenges and opportunities, and their exploration could lead to the discovery of various forms of time crystals, each with its own set of properties and applications.
Challenges and controversies. Despite their promising potential, time crystals face significant challenges, particularly concerning their stability and scalability. The main question revolves around whether these states can remain stable under different physical conditions or over extended periods. Moreover, there is ongoing debate among scientists regarding the exact conditions necessary for the formation and maintenance of time crystals. These discussions are crucial as they direct the future course of research and the practical realization of time crystal-based technologies.
Analogies and simplified explanations. To demystify the complex nature of time crystals, one can think of them as a metronome that never stops ticking or a clock that keeps perfect time forever without winding. These analogies, while simplified, help illustrate the idea of perpetual motion in a non-equilibrium state, which is central to understanding time crystals. However, it's crucial to note that these are not perfect comparisons, as the actual physics of time crystals involves more intricate quantum mechanical processes.
The theoretical description of time crystals is grounded in sophisticated mathematics, involving advanced quantum mechanics and theories of condensed matter physics. The Hamiltonian of a system, which describes its total energy in the case of time crystals, includes terms that account for their time-periodic behavior. Understanding this mathematical framework is essential for furthering our theoretical and practical knowledge of time crystals, and for exploring their potential applications in various technological fields. The creation and observation of time crystals require precise experimental setups. Techniques commonly employed include the use of lasers to trap and cool ions or atoms to near absolute zero, creating the ideal conditions for the formation of time crystals. These setups are complemented by advanced measurement tools that can detect and analyze the periodic oscillations characteristic of time crystal states. These techniques are not only crucial for studying time crystals, but also for verifying theoretical predictions and exploring potential applications. Disorder plays a surprisingly constructive role in the stabilization of time crystals. In systems like trapped ions, slight variations in ion positions can help sustain the time crystal state by preventing the system from thermalizing. Similarly, interactions between particles, such as the spins of electrons, are critical for the formation and stability of time crystals. These factors ensure that time crystals can maintain their unique properties under various conditions, making them more viable for practical applications. Just as water can exist as ice, liquid, or vapor, time crystals can manifest in different phases. There are discrete time crystals, which oscillate at fixed intervals, and continuous time crystals, which show more complex continuous changes over time. Each type of time crystal has distinct properties and potential applications, and understanding these phases is crucial for harnessing their capabilities in various scientific and technological domains.
The potential technological implications of time crystals are vast and varied. In quantum computing, for example, they could lead to the development of more robust and error-resistant qubits, potentially revolutionizing the field. In materials science, time crystals could inspire the creation of new materials with novel properties, useful for advanced sensing and communication technologies. These applications are just the tip of the iceberg, with many more possibilities likely to emerge as our understanding and capabilities evolve.
The implications of time crystals extend beyond physics and technology. In biology, for instance, understanding the behavior of time crystals could provide new insights into biological rhythms and cycles, such as circadian rhythms. Additionally, the study of time crystals could enhance our understanding of other materials and phenomena, leading to cross-disciplinary innovations in fields ranging from neuroscience to environmental science. These interdisciplinary impacts highlight the broad relevance and potential of time crystal research in solving complex problems across various domains.
Time crystals often evoke images of perpetual motion machines and other impossible phenomena, leading to misunderstandings about their nature and capabilities. It's crucial to clarify that while time crystals exhibit perpetual motion-like behavior at the quantum level, they do not violate the laws of thermodynamics and are not capable of performing work. Engaging with the public to correct these misconceptions and explain the real science behind time crystals is essential for fostering a better understanding and appreciation of this exciting field.
The field of time crystals is rapidly evolving, with new research papers and breakthroughs being reported regularly. These include novel experimental setups and the discovery of time crystals in different materials and conditions. Additionally, collaborative efforts between various international research teams are enhancing the pace and scope of time crystal research, promising exciting developments in the near future. Keeping abreast of these advancements is crucial for anyone interested in the cutting edge of science and technology.
Time crystals are not just another new material, they are a challenge to established physics paradigms. They force us to reconsider our understanding of time symmetry in quantum systems and have implications for fundamental theories of matter and energy. By pushing the boundaries of how we conceptualize and study matter, time crystals are helping to expand our theoretical frameworks and could lead to new principles and laws in physics.
As we continue to explore and understand time crystals, their full potential is just beginning to be uncovered. With their ability to maintain perpetual motion and their implications for technology and fundamental physics, time crystals represent one of the most fascinating frontiers in science today. The journey from theoretical speculation to experimental realization and beyond is a testament to the relentless pursuit of knowledge and the ever-expanding possibilities of science. As research progresses, the future of time crystals is not just about new discoveries, but about redefining the very fabric of reality. By diving deep into the world of time crystals, we are not just observing a new kind of material, we are witnessing the unfolding of a new chapter in the story of science.